Welcome to Georgia Tech. My name is Professor Matthew Higgins. If you are listening to this video, that means you have been accepted to the Executive MBA program. Congratulations. This math review is intended to help you get ready for your fall semester. It's not going to teach you math, but the goal is to help blow the dust off some math skills that you might have acquired years ago. By now, you should have received a book by Trevino called an MBA, Pre-MBA Analytical Primer, along with a file that has 6 documents. The first will be a document that just says read me, and it's a letter from me welcoming you and providing an overview of the chapters of the book that I would recommend that you take a look at. In particular, the first 2 chapters of the Trevino book. Uh, the book is pretty good. There's also going to be chapters on statistics. So prior to your statistics class, if you have not ever had statistics or it's been a long time, I would recommend that you look through that chapter prior to class. It'll also serve as a good reference for you during that sequence. Also in the spring, you'll be taking corporate finance. The book has a nice chapter getting you ready for corporate finance, refreshing your memory on things such as the present value of money. The second document that you should get or you should have will be this PowerPoint. And I designed this PowerPoint to go very closely with along with the book. I'm not, that's intentional. So if you're caught up on something in the slides or something that we're talking about here, you can look at the book, or if you're looking at something in the book, you can find where we're talking about it here in the slides. The third and fourth document are a set of review questions and then a set of detailed solutions. If you can work through those 10 questions, you should be sufficiently prepared for any math that you'll certainly have in economics, and I would probably say the rest of the program. In general, we're talking about basic algebra, and we're going to be talking about basic calculus. And when we're talking about calculus, we're going to be focusing on simple first derivatives. We will not get into integration in economics. We'll talk about where one might use integration, but we won't necessarily do it. With today's computers, one would do it with a computer versus manually anyways. Um, the last 2 documents are, one of them is going to be a page with some links, online links. If after you get through this conversation that we're having, you read these couple chapters and you're still struggling, I'd advise you to check on those online links. In addition to those, and those are just sources that I had found on YouTube going over some of these same basic skills. Maybe somebody's presenting something in a different way that may make it a little more easy for you. The alternative that you also have is the Khan Academy. Khan Academy will go probably far more in depth in the material that you need, but it's laid out fairly well so you can jump into, if it's dealing with algebra, if it's dealing with functions or exponents or logs, or if it's calculus, thinking about simple differentiation. The Khan Academy has videos broken up that are fairly easy to understand. And then the last document in this package is another PowerPoint just focused on differentiation, and it walks through some of the rules um, that we have with basic differentiation. So combine, the intent of all of this is to try to get you up to speed. So when we jump into certainly economics in the fall, and statistics I believe you also have in the fall, you're not getting caught up on the mechanics of what's going on in class, and you can focus on what's being said. My contact information is on the very last slide. If you're struggling with the questions, or if you need an additional resource, please feel free to drop me an email. If you're struggling on a question, what I'd recommend you do is just scan your work and email it to me. And what I'll do is I'll print it out I'll write on it, or I'll try to comment on it and try to get you on the right track, and then I'll scan it back to you, and we'll see if we can't get everybody through those questions and answers and ready for the fall. Let's start and talk about basic concepts first. And when we in doing this, let's go back to basics and talk about variables and functions. I've got a red pen down here that you're going to see me. That's me with the cursor. I've got a red pen. I'm going to mark these slides up as we go along. So when we talk about variables in math, okay, variables nothing more than a letter or a Greek symbol that we're going to use to represent something that we don't know. And it can be some quantity. In economics, we're going to be thinking a lot about quantities of things. And in general, we're going to start by using the letters X and Y. But that does not mean that we can't use any letter or any Greek symbol. So just two simple examples here. We say a light bulb manufacturer who produces X units has a total cost of production of Y dollars, or a salesperson who sells X number of cars per month receives a salary or a monthly commission in Y dollars. Okay, so these are examples of different variables. Okay, and ultimately these are going to be quantities that we're going to want to quantify. When we have multiple variables, and in this case, in these two examples, okay, this is going to lead to a particular function. So when we can mathematically quantify this light bulb manufacturing equation. Okay, ultimately, if we're interested in how many light bulbs they produce, which is X, we can figure out their total production cost, Y. So when we think about a function, think about a function as a black box. Okay, you're taking some data and you're throwing it in that black box, and in that black box is spitting out some output. So if we went back to this light bulb example, we could create a function where we would input the quantity X of light bulbs that are being produced, and that function would kick out Y, the total cost of production. And we'll talk about where we get functions from and how we create these things. When we talk about functions, okay, we're going to be able to write these down into an equation. We're going to call typically variable X, or the variable that represents the input, our independent variable, and that's typically represented by X. The variable that represents the output is typically called the dependent variable, and this is typically expressed as Y. Okay, you'll often see very basic functions written as Y equals f of X, so that's f parenthesis X. Okay, and when you see that linear equation, you see the dependent variable on the left-hand side and the independent variable X, some function of X, on the right-hand side. Here's a couple examples. So say we've got the first function, it's just Y equals f of X, and f of X equals 2X minus 1. So we've got Y equals 2X minus 1. So if X equals 3, so let's assume this is that light bulb example. So if we produce 3 light bulbs, so X equals 3, we're going to plug 3 in for X, and we get 2 times 3, which is 6, minus 1 equals 5. So if this were that light bulb example, the input X would be the number of light bulbs we produced, and if we put X into the equation, we get Y equals 5, so we would get a production cost of 5. The second example, we've got Y equals f of X, or equals 60 minus 2X squared. So in this case, if we put X equals 5, okay, we've got 5 squared, which is 25 times 2. Okay, so we get 60 minus 50, which is 10. And the third example that we have here is Y equals f of X, where Y equals 20 plus 2X. And if X equals negative 1, what do we have? So we've got 2 times negative 1, so that's minus 2. 20 minus 2, we get a value of 18. Let's put this in the context of economics. Since I teach economics and you'll have this class with me in the fall, let's use an economics example. So let's think about a revenue function. So let's use this. Let's say we've got a small firm that produces widgets that are sold in the market, and the firm's price is $2 per unit. Okay, we're going to denote the number of widgets sold by Q, and the firm's sales revenue by R. Okay, sales revenue is calculated as P times Q, units sold times price. Okay, the relationship we have here is that R is going to be the dependent variable. Okay, and that's revenue, and it's a function of Q. Okay, and Q is going to be quantity or the units sold, and that's going to be the independent variable. So we've got R equals F of Q equals 2Q. So in this example, R is taking the place of Y. Okay, and what's important is that R is on the left-hand side. Whatever variable is on the left-hand side will be your dependent variable. It's most often Y. In this case, we're just using R. So we get a revenue function that's a function of 2 times the quantity produced. So let's assume now that the firm sells 1,000 widgets. So if Q equals 1,000, so we'll put 1,000 into our revenue equation. That's 2 times 1,000. We're going to have a revenue of $2,000. This is a very, very simple revenue equation, and no revenue equation looks like this, but you get the point. Okay, what we've got in this case are two variables, R and Q, and we've set up as a function. We've got some black box. That black box relationship is 2 times Q. All we need to do is put in our input, which is Q, and it'll give us our output, which is revenue. More realistically, we're going to be dealing with, or you will be dealing with, or we will be dealing with what are called multivariate functions. Okay? And all a multivariate function is a function that has more variables than just x. So let's say y is going to depend on 3 variables, x, w, and z. So, we can go to an extreme example. Let's assume y is the new Boeing Dreamliner. Its construction, we could write a multivariate function for the construction of the Dreamliner. So y would be a completed plane, and that function on the right-hand side would have tens of thousands of variables because you've got tens of thousands of different components and pieces that go into the construction of that plane. Very, very hard to do with pencil and paper, but a lot easier to do and practical to do, or possible to do with computers. So let's start with this multivariate function. So now we've got a function that's y is a function or y of x, y, or I'm sorry, x, w, and z. We've got let's go through this example on the bottom. So we've got y equals 5x plus 3w minus 2z minus 4. Okay, that's our black box function. And we'll talk about in a second where we get these, where we derive these functions from. So if we go out and we find out that x equals 2, w equals 0, and z equals 1, what do we have for y? Well, if we take 2 into that equation, 5 times 2 is 10. If we take 0 into that equation, we got 3 times 0, that's 0. If we put z equals 1, we get 2 times, or negative 2 times 1, and we get minus 2. So we've got 10 plus 0 minus 2 minus 4, which, if my math is correct, should be 4. So let's spend a minute where, let me get my red pen out. Let's spend a minute and figure out where we get this equation, these multivariate equation from. In particular, where we get these coefficients from. Okay. These coefficients are going to be derived from statistical analysis or regression analysis. We can go out. Let's use the extreme example of the Dreamliner. We can think about what it's going to take to construct the plane. I mean, we can envision the final product, and then we can look at all the inputs. Okay, and the various amounts and various ways that those components can be put together. Okay, we can form a statistical relationship and through regression analysis come up with come up with the functional form. Okay? There's a problem. Okay, one needs to always be very, very, very careful when doing putting together multivariate functions. Okay, so for example, two ways that multivariate functions are being put together. In this case, the first example using big data. So UPS is trying to figure out when they're trying to preemptively figure out when their trucks are going to break down. Makes sense. So they're using predictive analysis. So the dependent variable y is just simply 1 or 0. Is the truck going to break down? And we're going to be looking at the probability that a truck breaks down. And it's going to be a function of all kinds of things on that right-hand side. So when they're saying, I have highlighted here in blue, they're collecting data from hundreds of sensors in each vehicle. You have got a multivariate function that has hundreds of variables on the right-hand side, and it is all trying to preemptively predict whether that truck will break down. Okay. Another example where people have used here, this is using Google Trends, and here what they're trying to do is trying to predict equity price movements or stock price movements. So in this case, the dependent variable on the left-hand side would be equity price, and on the right-hand side would be anything that they are, in this term, they're just searching terms. Um, and again, this is a multivariate function. But think about these last two examples. On the one hand, UPS is using sensors and they're collecting data. And in this case, this was a study, but people are using search terms from Google. This is probably looking at news and what people are searching for and things like that to try to predict equity movements. Okay, so you can again take all the data, run a regression analysis, and get, even in this case of the UPS example, and you can get a multivariate function. But always remember, correlation is not causation. And what you get in a multivariate function from at least, those last two examples is correlation. Okay, so here's a silly example. Okay, and this is just simple correlation. I could write a multivariate function that relates global average temperatures with the number of pirates. This is certainly a silly example, but it proves the point. So I mean, if we were to actually look at this graph, it actually looks like as the number of pirates go down on the x-axis, the global temperature goes up. So if you want to decrease global warming, somebody saw this table, and naively you would say, we need more pirates, and global warming would go down. Here's another silly example. And this is a multivariate. This is a function where we've got plotting, where we're plotting. What are we saying here? We're saying that organic food sales cause autism. And you've got, if you look at here with this R value, 0.997, that's a measure of fit. Okay, that's basically saying there's a 99% relationship between organic food sales and autism. Which if you just naively looked at this graph, you'd say, look at that. Okay, this is, organic food sales cause autism, and that's not what we're trying to say. Okay, these are silly examples, but the point is the same. Correlation is not causation. Okay, one final example. This one is an Apple user. I actually believe this one, so I will buy the snake oil. And this relates to the market share of Internet Explorer and the murder rate. So as the Internet Explorer's market share has declined, the murder rate has decreased. So if we thought that this was causation, we would just simply say we would have no murders in the United States if Microsoft went out of business. Remember, correlation is not causation. And in these examples, these were just spurious regressions. When you're writing multivariate functions or thinking about multivariate functions, you have to have some theory as to why you've got particular variables in that regression. So go back and think about the example with the Dreamliner. If we're producing a plane on the left-hand side and on the right-hand side are inputs, all of those inputs should be relevant to the construction of that airplane. You wouldn't put random things on that right-hand side. Otherwise, you're just going to get a spurious and biased relationship. Let's now put this in the context of supply and demand. So we've been using I just had some silly examples, and then we were using the example of the Dreamliner. But let's put this in context of supply and demand, since this is something you'll see in the first semester in economics. So we're going to look at supply and demand. So first we're going to look at demand. And in this case, we're going to think about all the different or several different factors that may affect a consumer's willing to purchase your product. Okay, so let's just say in this case, we've got three variables that are going to affect whether somebody's interested in purchasing or demanding your product. So QD is going to be quantity demand for a product, and we're going to say it's a function of three things. P, which is the price of the good, PA, price of alternative goods, and income I. So let's say this is demand for Tesla. And so P would be the price of the Tesla, and price of an alternative good, maybe it's the BMW or something like that. And then certainly your income. And then we're going to have an equation, 200 minus 3P plus 4PA plus I. And let's say that we gather data and we know that the price of our good is $4. We're no longer talking about Tesla, but the price of our good is $4. The price of an alternative good or our competitor's good is $3, and let's say income is $100. Okay, we can figure out how much quantity or how much demand there will be by an individual consumer. So we got 200 minus 12 plus 100, and that's going to be 300 units of your good. Companies spend a tremendous amount of money trying to figure out, first of all, who is interested in purchasing their product, and then conditional on the consumer wanting to purchase their product, what variables determine how much or their demand for their product, and then ultimately trying to understand what demand for their product will be, because that affects things like not price, but that affects things like production, and also what a firm might be able to do in terms of advertising, in terms of making that consumer more brand loyal, or increasing overall demand, getting it, trying to figure out, if I can figure out what the people who purchase my product, what characteristics they have, I can go out and search and try to find other consumers that look like them but might not know that my product exists, and bring them into the product market. Just like we did with demand, we're going to be able to do the same kind of analysis with supply. Okay, we've got a multivariate function. Here we've got the quantity supplied, QS, is a function of P, PM, and PT, where P is the price of the good. Okay, PM is going to be input material cost, okay, or our input price. And PT is we'll just say the price of some technologically related goods. Okay, and we've got now our multivariate function, 10p minus 2pm minus pt. And again, let's say the price of our good is $15. Input price PM is $10 per unit, and the related product price is $30. So if we put all that into our supply equation, we get 10 times 15 minus 2 times 10 minus 30. And given those prices, we would produce, or your firm would be willing to produce 100 units. Okay, let's look for a moment where with this supply function of the three variables, the three independent variables on the right hand side, P, PM, and PT. PT is pretty easy. That's just observing out into the marketplace. You need to know, in this case, all you need to know is who your competitors are, and you should be able to observe their price. A little more difficult when you're dealing with one-on-one contract negotiations, and contracts are private. So if we use the example of, say, medical device contracts with hospitals, Often those contracts will have contractual language in there that makes the revelation of price illegal. So it may be very difficult or more difficult for you to observe the actual price of a competitor's goods. Of all these prices, input price PM, you should have a pretty good handle on. Most firms have accountants and pretty good idea of costs, okay, and that'll go into PM. And then we'll talk about where the price of the good comes from in class. We've got two multivariate functions, and we've got supply and we've got demand. Okay, we've got one where QD, let me flip back to QD, 2 slides here. Here, the quantity function, demand is a function of price, and look at this. What we have here is a negative sign. So quantity demand is going to be negative related to price. Think about your own life for a minute. If the price of something goes up, or if the price of something continues to go up, the quantity that you demand for that product is going to go down. Okay, so what we're going to say is that the demand function is negative related to price. Okay, likewise, quantity supplied is going to be positive related to price. Let me go back to this slide. So here we go, quantity supplied, and look at P. 10p is positive. So what this means is the price of something goes up, okay? The quantity supplied of that product should go up. Think about what's going on in the global oil markets right now. In the global oil markets right now, I mean, forget about what's happening on the demand side. Demand globally is pretty weak. A lot of the discussion is all on supply. You've got countries like Libya and Iran coming online and producing oil, and you've got the U.S. just called North American energy revolution, where with shale and oil sands, we're producing a lot of oil. So you have a tremendous amount of supply coming onto the market. It has driven price down. And as a result, if price goes down, you got a positive relationship between quantity supplied and price. As price has gone down, we've seen supply slowly begin to come off the markets. In the case of the United States, you've got shale production wells coming offline, and you've got OPEC talking about trying to restrict supply. So again, this is just a positive relationship between price and quantity supplied. I'm going to come back to this supply and demand example, but before we do that, we need to have a side discussion on linear functions. Okay, let's write an equation. So in this case, we've got 8x plus 1 equals 2x plus 13. So we've got different colors here on the screen. Let me grab my red pen. So we have a linear function, and first of all, this is called a linear function because there's no exponents on x. So anytime we have an equation and there's no exponents on x, it's going to be a linear function. Let's talk about some terminology. So we've got an equality sign here. Anything to the left of the equality, okay, this is the left-hand side, LHS. So when we talk about things on the left-hand side or moving stuff from the left-hand side, all we're really talking about is what's over here on the left side of the equality sign. When we talk about anything that's over here on the right-hand side of the equality sign, we're talking about the right-hand side. So if we talk about moving 8x to the right-hand from the left-hand side to the right-hand side, all we're really talking about is moving it from this side of the equality sign to this side of the equality sign. Let's talk about the terms that are in purple here. I think these are in purple. Okay, these are going to be constants. So number 1 and number 13 are constants. Okay, each one of these, we've got 4 terms. So we've got a term which is 8x, 1, 2x, and 13. So this is a linear function with 4 terms, 1, 2, 3, 4. Let's talk about this first term. This first term has a coefficient and a variable. So in this case, 8x. So x is the variable, and we've got another variable x over here, and we have two coefficients in this equation. We've got the coefficient 8, and we've got a coefficient 2. So anytime we talk about a coefficient, you know that it's a number associated with a variable. So it is a term that will have a variable in it. Linear functions take the form y equals a plus bx. Okay, and again, there's no coefficient on x. That's what makes it linear. If there was a coefficient up here, if this was squared or something, we would call this a nonlinear function. And we'll talk, and I'll show you what those look like. The term a, or the term a is a constant, and the coefficient b is a constant, and in a linear function we're going to limit b not equaling to 0, because if this was 0, then this would just be y equals a, just a constant. Linear equations or linear functions are going to be written in two forms. We're either going to say the functional form is explicit or it's implicit. When we talk about an explicit linear function, that just simply means that the equation is y on the left-hand side all by itself, and a plus bx and anything else is on the right-hand side. Okay. So when we say explicit linear function, just remember y, the dependent variable is by itself, and every other term is already on the right-hand side. An implicit function will usually have all the variables grouped together, in this case on the left-hand side of the equation, equaling usually some constant. Okay, so in this case, A, B, and C are constants. You've got the coefficients A and B, and we've got variables X and Y. Okay, in order to transform an implicit linear function to an explicit linear function, what we would do is we would move AX to the right-hand side, and then we'd have to divide by B. And in most cases, we're going to be, especially in economics, we're going to be dealing with explicit forms of linear functions. Once in a blue moon, we'll deal with implicit functions. We're going to have a couple sets of rules for linear functions, and then we're going to go through some examples. Okay, so the first rule that we have is that we can move a term from one side of the equation to the other, okay, and its sign is going to change to the opposite signs as it crosses the equality sign. Okay, so let's go back. Let's go back here. So let's say we've got this implicit equation, and we've got ax plus by equals c, and we want to move ax to the right-hand side. Well, this is a positive variable, okay, or a positive term. So in order to get this from the left-hand side to move it to the right-hand side, we need to subtract ax from both sides of the equation. So if we put ax minus ax, okay, plus by equals c minus ax, what that's going to do on the left-hand side is positive ax minus ax. That becomes 0. And then what we're left with is by equals c minus ax. The second common rule that we're going to have is multiplying or dividing both sides of the equation by the same non-zero number does not alter the equation. Okay. Let's do a couple examples. So let's say we've got this implicit functional form ax plus by equals c. Let me get my pen again. So we've got ax plus by equals c, and we want to get this thing into an implicit form, okay, which just means that y equals y on one side and then everything else on the other side. So let's start ax plus by plus c. So the first thing we want to do is move ax to the right-hand side. So as I just said on the previous slide, we've got positive ax, so we're going to subtract each side of this equation by minus ax. And when we do that, on the left-hand side, what we're left with is by equals c minus ax. Now we still have a coefficient b over here, and in the explicit functional form, we want just y all by itself. So we need to divide each side of the equation by b. So we're going to divide each side of the equation by b. Any number divided by itself equals 1. Okay, so that's how that goes away. And what we're left with is y equals c minus ax divided by b. And we can write this, we can even write this into two terms. So we've got a common denominator. So we can write this as c divided by b minus ax divided by b. Okay, so we took the implicit form of a function, and what we've got now is the explicit form. Let's talk about inequalities, linear inequalities. So what we're doing now, let me get my pen again. What we're doing now is removing the equality sign and making this either a strict inequality or just an inequality. Okay, so if we have the form ax plus b less than or equal to, that's what this sign means less than or equal to cx plus d. Okay, this is going to be an inequality. Okay. Or if we have ax plus b is strictly less than cx plus d. Okay, we're going to call this second term a strict inequality. So when we say just the verbiage inequality, what we really mean is less than or greater than or equal to. Okay, in this case, less than or equal to. Okay, when we talk about strict inequality, what we mean is just strictly less than. So in this case, ax plus b is strictly less than cx plus d. Okay, in this case, a, b, c, and d are just constants. X is a variable. We've got a couple rules with linear inequalities that we need to talk about. Okay, so the first rule, if the same number is added or subtracted by both sides of the inequality, the resulting inequality has the same direction. Okay, so let's start with 2x plus 4. Let me get my pen. 2x plus 4 is strictly less than 3x plus 5. So in this case, let's move 4 from the left-hand side of the equation to the right-hand side of the equation. So in order to do that, we've got positive 4 here, so we need to subtract 4 from both sides. So we're going to do that here. So we've got 2x plus 4 minus 4, so these terms cancel out. Still strictly less than 3x plus 5 minus 4. So we're left with 2x is strictly less than 3x plus 1. Okay. Rule number 2, if both sides of an inequality are multiplied or divided by the same positive number, the resulting inequality has the same direction as the original inequality. Okay, so let's get our pen again, and let's say now we've got 2x is strictly less than 3x plus 5. So in this case, we want to get rid of this 2. So in order to get rid of 2, we're going to divide each side of this equation by 2. And when we do that, any number divided by itself equals 1. Okay, so we divide each side by 2. These 2 cancels, and what we're left with is x is strictly less than 3x plus 5 divided by 2, or we can write this as 3x. Let me see if I can do this so you can read it. 3x divided by 2 plus 5 divided by 2. So 5 divided by 2 is just 2.5. 3x divided by 2 is just 1.5x. Okay, but the point of this is we divided by a positive number, and this strict inequality did not change directions. Rule number 3. Okay, if both sides of inequality are multiplied or divided by the same negative number, the resulting inequality has the reverse direction. So now look at this first equation. See, this inequality goes from strictly less than to strictly greater than. And that's going to happen because we're going to divide by a negative number. So in this case, we want to take negative 2 from the left-hand side and get it over to the right-hand side. In order to do that, we need to divide by negative 2. And when we divide by negative 2, the minute that we divide by a negative number, this inequality sign flips. So now we go from negative 2x is strictly less than 3x plus 5 to x, okay, is greater than, strictly greater than 3x plus 5 divided by negative 2. Okay? Or again, we can say this equals, oops, so negative 2 and negative 2 go away, and we can have 3x divided by negative 2 plus 5 divided by negative 2. Okay, 5 divided by negative 2 gives us negative 2.5. 3x divided by negative 2 gives us minus 1.5x. Okay, so the point of this slide again is the minute that you divide or multiply by a negative number, that inequality sign flips. Okay, in economics, you're going to realize this pretty quick. If you forget to do that and then you start trying to graph or think about what's going on, not reversing that inequalities will generally give you a really funky answer. Let's talk about inequalities and interval notation. So let's look at the right hand first. Let me grab my pen again. So we've been talking about inequality. So here we've got, let's look at this fourth term. This is strict inequality. We've got A is strictly less than X, which is strictly less than B. And let's look at this first term. We've got a regular inequality. A is less than or equal to X, which is less than or equal to B. Okay, so let's read down these inequalities first, and then we'll talk about interval notation. So this first inequality we've got is A is less than or equal to X, which is less than or equal to B. The second inequality we've got A is less than or equal to X, which is strictly less than B. Okay, the third one is A is strictly less than X, which is less than or equal to B. The fourth one is A is strictly less than X, which is strictly less than B. The fifth one, we've got X is less than or equal to B. The next one is X is strictly less than B. The next one is X is greater than or equal to A. And then finally, X is strictly greater than A. Okay, so this is inequality form, but there's also another way that we can denote these same things, and this is called interval notation. In interval notation, you're going to see, if you look over here on the right-hand side, you're going to see brackets and you're going to see parentheses. Okay, parentheses are going to be used for the equivalent of a strict inequality. Okay, so when we look at a strict inequality, let me draw a little arrow over here. Okay, that's going to correlate with a parenthesis. When we're talking about an inequality, in this case less than or equal to, we're going to be using a bracket. So if we were to read this first inequality again, A is less than or equal to X, which is less than or equal to B. If we write that in interval notation, we'll write a bracket A, comma, B bracket. What this means is that X, or A, is less than or equal to X, which is less than or equal to B. Okay, so these brackets are equivalent to the equality. Now let's look at this second case. The second inequality on the right-hand side, we've got A is less than or equal to X, which is strictly less than B. Okay, so if we come over here in interval notation, since this is less than or equal to A, or I mean A is less than or equal to X, we'll write bracket A, comma B, but now we're going to write a paren. So what that means is that A is less than or equal to X. Okay, you can think of this comma as X. So A is less than or equal to X, which is strictly less than B. Okay. Let's go down to this fifth example down here, where X, we just have one side of the equation. So this is just X is less than or equal to B. Okay. When we come over here to interval notation, you'll see that we have now the infinity sign. Because if X is less than or equal to B, that means that X can be from B to minus infinity. Okay, the first thing that we need to know is when we talk about infinity. Okay, we will always, always, always use a parenthesis. You'll never use a bracket, because remember, the bracket means it could potentially be equal. Okay, and you can never be equal to infinity. It's mathematically impossible. So if we say x is less than or equal to b, we're going to just say that b, okay, x can go all the way from negative infinity, okay, up to b. Okay, so x is less than or equal to b, okay, and it can go all the way to negative infinity. Let's look at strictly x is strictly less than b. Well, now that we have strictly less than b, now we're going to have parentheses on both sides. They're going to have the parenthesis from the negative infinity, and now we're going to have a parenthesis up here with b. This just tells us that b, okay, or x is less than strictly less than b. Okay, it goes from b to negative infinity. We can do the same thing with positive infinity. And again, positive infinity is going to be always associated with a parenthesis, never a bracket. So x greater than or equal to a. So since it's an equality greater than or equal to a, we're going to use the bracket. That just means that x is greater than a, greater than or equal to a, goes from a, could equal a, but it goes from a to positive infinity. In the last case, we've got x is strictly greater than a. So we're going to use, since this is a strict inequality, we're going to use the bracket. Okay, we'll use the bracket on a, and it can go from a to positive infinity. And sometimes you'll see people, even though this is over here, you'll see a positive sign for completeness. Okay, sometimes they'll just use the negative sign for negative infinity. So if you don't see a positive sign, it means positive infinity. Okay. Interval notation isn't as common in economics, but you could see it. I mean, we could use it in class. I won't. You will often see this you could see this in stats. Let's do a couple examples. So let's start with 3x plus 2. Let me grab my pen. 3x plus 2. 3x plus 2 is greater than or equal to x plus 8. So this looks like we're going to move, what are we going to do? We're going to solve for x. So we're going to take x from the right-hand side and move it over here to the left-hand side. In order to do that, we've got a positive x. So we're going to, step number 1, let me see if I can make it number 1 here and circle it. There we go. Step number 1 is going to be subtract x from both sides. And when we do that, 3x minus x is 2x plus 2. Okay. Greater than or equal to, this goes away, and plus 8. Okay. Now we've got, so let's put this over here. 2x plus 2 strictly or greater than or equal to 8. Okay. Now since we've got a constant over here, let's bring 2 over to the right-hand side, because then we'll isolate 2x on the left-hand side. This is a positive 2, so in order to do that, we've got to subtract 2 from both sides, which we do here. And if we do that, this term goes away, and we're left with 2x greater than or equal to 6. Now we want to get this 2 over from the left-hand side to the right-hand side. So we're going to divide each side by 2. When we do that, 2 divided by 2 goes away, and we're left with x greater than or equal to 3. Okay, so we can write that as x as an inequality. X is greater than or equal to 3. Or we can write this in interval notation. Okay, we can write, since it's greater than or equal to 3, it'll be a bracket 3 going to positive infinity. And remember, since we're using infinity, it can never be equal to, so it will never be a bracket. We've got to use a parenthesis. Let's do one more example. So now let's start with, let me grab my pen, let's start with 3x, minus 3x, sorry, plus 2, greater than or equal to x plus 8. Let's do this. Let's do the same thing. Step number 1 is we're going to bring x over here, And then step number 2 is we're going to bring 2 over here. Okay, so this will be step 1. Whoops, put a new 1 there. And this will be step 2. That's a 2. So let's bring x from the right-hand side to the left-hand side. This is positive x. So the first thing we need to do is to subtract x from both sides. So when we do that, we've got minus 3x minus x. So that's minus 4x plus 2 is greater than or equal to 8. Okay. Now we want to bring 2 over the right-hand side. In order to do that, this is positive 2, so we need to subtract 2 from each side. And when we do that, this term goes away on the left-hand side. We're left with minus 4x is greater than or equal to 6. Now we need to bring minus 4 from the left-hand side to the right-hand side. But remember, we've got a minus sign there. So the minute that we divide by negative 4, what do we have to do? We've got to flip the inequality. So we divide each side by 4. Okay. Minus 4 divided by minus 4 goes away. We flip the inequality, and then we've got 6 divided by minus 4. Okay, so now what we've got is x on the left-hand side. X is less than or equal to minus 1.5. Okay, so there's our inequality form, or we could write that in interval notation. Since this is less than or equal to minus 1.5, we'll have a bracket. We'll have a bracket over here. And since this is an infinity, we'll have a parenthesis over there. Welcome back. I hope you're not listening to this straight through. Please don't. Actually, what I would advise you to do, I'm trying to do this in this discussion in sections. The homework problems or the review questions actually flow pretty consistent with this slide deck. So as you see, as you hear these breaks in the discussion here, you could stop after each one of these sections and try the review question. Okay, so we're coming back to our linear equations. We need to talk about slopes and intercepts. Okay, because ultimately, when we plot when we draw a linear equation, we're going to get a line. So in discrete cases, the Greek term delta is used to denote change. So when we say delta x, that just means a change in x. So when we use delta, it's going to denote a change in the value of a variable. Okay, thus a change in the variable x from x1 to x2, we can express that as delta x would equal x2 minus x1. Okay, let's say suppose that y is a function of x, okay, given by y equals f of x. The rate of change of y with respect to x is going to be the ratio of delta x and delta y. So the ratio of change, so ratio is just one number divided by another. So a ratio of change, delta y divided by delta x, what that equals to, well, y equals f of x, so it's going to be f of x2 minus f of x1 divided by x2 minus x1. Okay, and what I just said right here is the slope of a line. Let me put this in a different way. Maybe this will ring a bell from way back in math. The slope of a line is rise over run. Okay, that's where we're going. Let me grab my pen because I put a lot on this slide. So let's start with a linear equation or a linear function up here. Y equals a plus bx. Okay, a and b are constants. Okay, x and y are variables. Remember, b has to be non-zero. Whoa. Sorry. When we talk about a line, okay, we're going to have y, okay, on the left-hand side, x on the right-hand side. A is going to be the vertical intercept, okay, and b is going to be the slope of a line. So let's let's draw a y-axis and an x-axis. Okay, so if we're gonna graph something, we're gonna draw these blue lines. This is the y-axis, the vertical axis, and x is the horizontal axis. So when we talk about vertical intercept A, okay, that just means if we were to go over here, if x is 0, we're asking where does this line intercept the vertical or y-axis. Well, if we come over here and make x 0, y equals a. So this vertical intercept, this point right here, is a. It's a bad a, but that's a. Okay. The slope of this line, okay, is going to be the slope, and we can do the same thing down here with the horizontal intercept. The horizontal intercept is what happens if y equals 0. Okay, that's this point. Okay, we can figure that out. Let me see if I can do that over here. If y equals 0, then we've got a plus bx. Okay, we need to get x all by itself. So I'm going to move 0 to the other side for the moment. So I'm going to write bx plus a equals 0. Move a to the right hand side. So we're going to subtract a from each side. So we got bx equals minus a, because I had to subtract a from the left-hand side, which means I had to subtract it from the right-hand side, and now I need to divide each side by b. Okay, so this horizontal intercept point right here, that point is minus a divided by b. Okay. Let's come back up to b. B is the slope of the line. Okay, so the slope of the line is rise over run, okay, which is just the change in y divided by the change in x. Okay, the change in y is y2 minus y1 divided by x2 minus x1. If b is positive, in this case this is positive, you would have a line that looked like this. Okay, because it's a positive sloping line. Okay, this line is downward sloping. So this line is actually y equals a minus bx. Okay, because b is negative, so we're going to have a downward sloping line. Okay. If a changes, okay, all we're going to have is a parallel shift of the line. That means this vertical intercept is changing. Let me give you an example in economics that we're going to deal with, and this is going to be the only a tractable case that we can do in 2 dimensions. Because when I'm going to tell you this, you're going to be like, Higgins, that's not realistic. So we're going to see this with consumers' budget constraints. So let me grab my handy dandy pen, and let's look at this. Let's look at this top equation. So we got px times x plus pz times z equals m. All this is I've got a consumer that consumes 2 goods, X and Z, and they've got an after-tax disposable income of M. So think about this for your case. What I'm doing is I'm taking your after-tax income and telling you in say a given month, you only consume 2 units or 2 different items. Certainly not realistic. Why are we doing this case? First, if we do a 2 good case, we can actually draw this. If I put 3 terms up here, we're now trying to draw this thing in 3 dimensions, and I don't want to do that. I can't do that. I'm bad drawing on PowerPoint. We could mathematically take every good that you consume in an entire year or even over a lifetime, okay, and put all those terms here on the left-hand side. So if you in a given month, so M says your disposable income for a given month, and you consumed 1,000 different items, we could put all those 1,000 different terms on there. You can't draw it, okay? But what we're doing in this case with 2 goods easily extends out to, your entire, what we'll call a consumption bundle. And that means just simply everything that you can consume. So while I'm using a too good case, don't say, Higgins, this is unrealistic, and not pay attention, because this is easily expanded up to your entire consumption set. We just can't draw it. Okay, so let's put this in the equation of a line. In this case, z is going to function as our y. So look at what I did to you, because you'll see this sometimes. I've renamed the vertical axis z. Instead of having y, I've named this thing z. And we still have the horizontal axis x. Whenever you see this, okay, whenever you see a vertical axis that has a different variable, that's the term that has to be on the left-hand side of the equation. Okay, the vertical axis is the equivalent of the dependent variable. Okay, so the first thing that we're going to do is get px over to the right-hand side. So we're going to subtract px times x over to the right-hand side. So we're left with pz times z equals m minus px times x. Next, I want to isolate z all by itself, the dependent variable all by itself. So I'm going to divide each side of the equation by pz. So this goes away. I'm going to divide each of these terms by pz. What we're left with is z. This is the equivalent of y. Okay. M divided by pz. This is a constant. You can think of this is the same as that a term. Okay, this is a constant. Minus px divided by pz. This is a ratio of prices. You can think of that as b. Okay, times x. We've got a negative sign here, which means the slope, or which means this line is downward sloping. Okay, the slope of the line is b. Okay, the slope of the line is minus px divided by pz. If, as I said before, so let me write this down. So we had a equals a plus b x. If a changes, it's just causing a parallel shift to the line. Okay, so in this case, if we had m, okay, changes to m right here. If m changes, all it's going to do is a parallel shift. Okay, a parallel shift of that line. Okay, so if income changes, in this case, since this is a consumption pattern, if income changes, this budget constraint, and all this budget constraint means this is the maximum amount that you can, given your budget, that you can buy. So if income changes, so let's say we're starting, this is our initial, this middle one is our initial consumption bundle. And let's say your income goes down. If your income goes down, your budget constraint, okay, the amount that you can buy goes down. So hopefully, by the time you get out of the exec ed program, your income does not go down. Okay, if it did, your consumption, your budget constraint would shift in. Okay, our hope is after the program, your income will increase. That would cause this thing to parallel shift out to the right. Okay, the point is that any changes in that constant a, or in this case m, will cause this budget constraint or this linear function to either parallel shift in or parallel shift out. If the slope changes, okay, if the slope changes, this linear function is going to rotate. So let's say we're here. Okay, so this is our initial point. And if the slope changes, that ratio of prices, and let's just say that the price of X changes. Okay, so let's think about what this intercept is. This intercept, what does this mean? You've got two goods, X and Z, and you've got an income M. If we consume no amount of good X or of good Z, that means this point right here is this quantity of X is simply our entire disposable income divided by the price of X, right? Because that's the only thing that we're consuming. Okay, so that's this point right here. So that's this point right here. Now let's say that the price of X changes and the price of X goes down. Well, if the price of X goes down, okay, the amount that you can consume is going to go up. So it's going to shift out over here. Okay, so if the price of X decreases and your income doesn't change, that means you can buy more of that good. So if this is beer, you can buy more beer. Okay, so this budget constraint is going to shift out. Let's say the price of X increases. Gas, say, oil prices go up, gas prices go up, and let's say it's the only good that you're consuming, your income doesn't change. But if the price of gas goes up, your budget constraint will this linear function will rotate in. And if you notice, this y-intercept did not move. All this is doing is is rotating this thing left and right. A couple side notes. Okay, the slope of a vertical line is undefined. That's this red line. Okay, the slope of a vertical line is undefined. Because think about the slope is defined as rise over run, change in y divided by change in x. Well, you can have a change in y, but what's the change in x? The change in x is undefined. Okay, or it's zero, which you can't divide by zero, which makes this undefined. Okay. The slope of a horizontal line, on the other hand, is just simply zero. Because remember here, let me write this. Let me grab my handy dandy pen. Okay, remember we have this as change in y. Oops, divided by change in x. Okay, so if we're going from here to here, okay, so this is x2, and this is x1. Okay, and then in the denominator, x2 minus x1 is defined. Right, those are numbers. Okay, here we've got y2 minus y1. This is equal to 0. Okay, well, you can have 0 in the numerator. You can have 0 in the numerator and a number in the denominator. That just makes this equal to 0. Okay, unlike up here where you had y2 minus y1 divided by x2 minus x1. Okay, this is equal to 0. Okay, you can't divide by 0, which makes this thing undefined. Okay, you'll see you will see this again in economics, because this has to do with we will talk about these. If these are demand curves, we will talk about these. So a really steep linear function like this is a consumer who is very brand loyal. So for those of you in the world of marketing or advertising, and you've got very brand loyal consumers, you've got a demand curve that is not perfectly, it's not perfectly up and down, but it's very, very steep. If you talk about consumers that are not brand loyal at all, that just means their demand curve will be relatively flat. So you'll see these again. Now, since we've taken this slight detour, we can come back to our supply and demand equations that we had, because we had two linear functions, and now we're going to combine them and solve for price and quantity. So let me get my pen. So let's draw a graph, and on the y-axis we're going to put price, and on the x-axis we're going to put quantity. And the downward sloping line that we had, right, was quantity demand. It was the negative relationship between quantity demand and price. If you remember, if price goes up, the amount that you demand of it's going to go down, or the quantity you demand is going to go down. And we're going to have an upward sloping quantity supply function. That just simply means as price goes up, firms will supply more. It's that positive relationship. So in the demand function, slope is negative. In the supply function, slope is positive. These lines will intersect. And at this intersection, this happens to be a market equilibrium. This will be the equilibrium price, and this will be the equilibrium quantity in an unfettered market. So let's assume that we've got, here's our demand function, here's a supply function. Okay, so let's say that our quantity demand equals 12.4 minus P, and we've got a supply function 1.3 plus 0.5 P. Okay, we know from the previous slide we're going to have an intersection where quantity supply equals quantity demand. Okay, we know they're going to intersect, so we can just set quantity supplied equal to quantity demand. So let's do that. So we're going to set quantity supplied equal to quantity demand. So we can do 12.4 minus P equals 1.3 plus 0.5 P. We need to solve for P. So in this case, I said I've decided to move P to the right-hand side. Okay, in order to do that, and then we're going to bring 1.3 over to the left-hand side. So we're going to add, since this is a negative P, we're going to add P to both sides. This is a positive 1.3, so we're going to subtract 1.3 from both sides. So here's our addition of P to both sides. I'm going to do that first. So we got 12.4 minus P plus P. Okay, so this term goes away, equals 1.3 plus 0.5 P plus P. That gives us 12.4 equals 1.3 plus 1.5 P. Okay, now let's bring 1.3 to the left-hand side. So this is positive, so we're going to subtract 1.3 from both sides. If we do that, we got 12.4 minus 1.3, that gives us 11.1 equals 1.5 P. Okay, now we need to get 1.5 P over here, so we're going to divide both sides by P. So if we do that, that gives us so if we divide 1.5, give it 1.5, whoops. We're going to divide by 1.5. What that gives us is 11.1 divided by 1.5 gives us a price. We've just solved for price, $7.40. So given a demand function that looks like this, a supply function that looks like this, they're both linear functions, okay, we're going to get an equilibrium price in the market of $7.40. Okay. Now the question is how do we figure out equilibrium quantity? This is easy. You're going to take, we just figured out equilibrium price when these things were equal, when supply and demand were equal. So you can plug price into either one of these equations and you'll get quantity. And which equation do you choose? The simplest one. So let's take quantity to demand because it's just easier. So we can say 12.4 minus price, 7.4, and then we're going to get an equilibrium quantity of 5. But you could put 7.4 in here. Okay, so 7.4 divided by 2 plus 1.3 will give us 5. So you've just solved for equilibrium supply and demand using two linear functions. Now let's have a conversation about exponents, because this is going to lead from our discussion on linear functions and allow us to say something about nonlinear functions. But in order to do that, we need to say something about exponents. Grab my pen. So we're going to say powers. Powers of numbers are variables. Okay, can be expressed using superscripts called exponents. In this case, x to the n. Okay, where the base is defined by x, or the variable, and the exponent is going to be n. Okay, we're going to have a few rules for exponents. Okay, so we're going to go through these rules, and the first thing that we're going to do is assume that x doesn't equal 0, because if x equals 0, no matter what any of this is, the answer is equal to 0. So the first rule, x to the 0, any number to the 0 exponent equals 1. Okay, so I mean, it doesn't matter what it is. This is just any time you've got an exponent where the exponent equals 0, that term equals 1. Second rule, okay, if we have x to the a exponent times x to the b exponent, so in this case we're multiplying two variables x that have different exponents. If we do that, what that allows us to do is actually just add the exponents. So the answer is, or what this becomes, is x to the a plus b. So if this were x squared, I'm just going to put a dot for multiply, times x to the 4th, okay, this just becomes x. I'm going to put a parenthesis up here, 2 plus 4. That's really bad. X, and that it just equals 2 plus 4 is x to the 6th. Okay. The third, if we have x to the a exponent multiplied by an exponent b. Okay, what we're going to do in this case, these exponents are going to be multiplied. So you'd have x a times b. So what this would look like is, say you had x squared to the third power. Okay, again, what that is just x. Now 2, put a dot there, times 3. And that equals x to the 6th. Let me erase this. I'm just gonna flip sides back, and there we go. Got a handy dandy pen. The fourth case. So now we've got x and z. We've got two variables to the a power. We can, in this case, so these are both variables, we can distribute the a exponent to each of the variables and multiply them. So now we've got x to the a times z to the a. Okay, or if we had this, we can pull the exponent out and write it like this: x times z times to the eighth power. A, not the number a power. Rule number 5, okay, this goes hand in hand with number 4. If you have x divided by z, again, these are both variables, times the power a, we can again distribute the exponent to the variable. So then we have x to the a power divided by z to the a power. So if we had x divided by z let's say 2, okay, we can just say this is x squared divided by z squared. There we go. Sixth rule, if we've got two variables that have exponents divided by each other, and the variable's the same, so in this case, a to the a power divided by x to the b power, we can subtract the exponents. So say we have x to the 4 divided by x to the 5. We can write this as x 4 minus 5, okay, or x to the minus 1 power. Okay. Number 7, and this will help with what I just wrote there. An exponent that has a negative sign, so x to the negative a, can also be written, that negative sign means that this should be in the denominator. So we could write that as 1 divided by x to the a. So if we write x to the a like this, and we don't want to write that as a ratio, we can bring this up. This is the equivalent of saying x to the negative a. Okay. So it means exactly the same thing. It just we might want to deal with this type of notation versus this type of notation. So what I just wrote here, this is the equivalent of x, 1 over x to the first power. Okay, that's all this is, which is just equivalent to 1 over x. So let's do a couple more examples. So here, just using some of the rules, let me grab my handy dandy pen. So we've got x to the third times x to the fifth. Since these are multiplied, we can just simply add the exponent. So this is x to the 3 plus 2, or x to the fifth power. Here we've got x to the squared multiplied or taken to the fifth power. So in this case, we're going to multiply 2 and 5. So this is x to the 2 times fifth power, or x to the 10th power. Here we've got x to the 8th divided by x to the 4th. Since these are the same variables and it's division, we'll subtract these two exponents. So we've got x to the 8th minus 2, or x to the 6th power. Let's talk about square roots or radicals. which ultimately will get us into fractional exponents. Okay, remember, this is going way, way, way back. So we got the radical sign, okay, or the square root. Okay, and square root is a form of a radical. So we got the radical sign. Okay, it looks like this. The radical sign. PowerPoint just doesn't have the, but that's what it looks like. The radical sign. Okay, it's going to be is an indicated root of a number or variable. So if we write the radical sign 20 or radical sign of x, okay, in this case, this is the square root of 20 or the square root of x. Okay. A positive number's got two square roots, and they're going to have opposite signs. So every square root we're going to have, so in this case, the square root of 9, or we could write this as 9 like this, that's fine, square root of 9, is both, you're going to have a positive and negative number. Okay, the principal square root is going to be the positive number. Okay, so if somebody talks about just tell me what the principal square root is, and we have the square root of 9, they just mean 3, not negative 3. And often you'll see just this shorthand. When they'll say the radical sign is used to indicate the principal square root. So if they want just the positive portion of the square root, they'll use the radical sign, okay, which will give you 3. If we want a negative, if we want the second square root, okay, so remember the square root of 9 is both positive 3 and negative 3. If I just want the positive 3, I just write the square root of 9, and that equals 3. If I want the negative 3, what I'll do is I'll put the negative number out here, because that says what's the negative of the square root of 9, and that's minus 3. Okay, so depending on whether I want the positive number or the negative root, I'll either have this as this radical as positive. Okay, this will either be positive or this will be negative. We're going to have rules here. So the square root of x times the square root of z. If we multiply two square roots, okay, we can bring that multiplication underneath the radical sign. Okay, so it's x times z, the square root of x times z. Likewise, if we have two square roots, two radicals that are divided by each other, we can bring that division within the radical. So in this case, we'd have x divided by z, the square root of that. Okay. The square root of 0 equals 0. Okay. The square root of a variable has to be greater than or equal to 0. Okay. If we get into this being less than 0, now you're getting into the world of I, or imaginary numbers. You will not see that in this course. That's a whole different batch of mathematics. Okay. If we have the square root of x cubed, okay, maybe if you remember, so let's go back to way back in your math day. So that x cubed is x times x times x, right? So we have two x's here, which means we'll bring one x out. Oops, x, which gives us x times the square root of x. That's the times sign. So we got x times the square root of x. Let's talk about fractional exponents. Okay. So let me write this let me write this x to the 1/2. Okay. So if we have x to the n divided by a, what we've got is a fractional exponent, which means the following. We've got the 8th root of x to the nth power. Okay, or we can write this as the 8th root of x to the n. Okay, so let me write this in the square root, because this is the root that we're most often just historically used to using. So that is x, and let me write the radical here. The a term, which is 2, this is the square root of x to the first power. Okay. So we could have x to the 3/4. we can write this as x cubed to the fourth root. Okay, so that's what the fractional exponent. That's how we write fractional exponents in radical notation. Let's do an example. And this example is going to be something that we're going to see when we get to producer theory. And producer theory, initially we'll be looking at the relationship between capital and labor, trade-offs between capital and labor. And we'll do some fun examples, and we'll talk about all this just automation and robots taking people's jobs and computers and things like that. So let's say we've got a production function, and we'll talk later where that comes from. And let's say we're using capital and labor. So we're going to call L labor, and we're going to use machines, and we'll call that K. And we're going to produce an output Q. And we're going to assume that this has a special functional form called a Cobb-Douglas production function, which is meaningless for the moment. But what that does is it gives us a function that says Q output equals 10 times L to the 1/2 power, or 0.5, times capital, or the number of machines, to the 1/2 power. And let's assume that this relationship between capital and labor for a particular firm is capital equals L divided by 4. Just simply, we need 4 workers per machine. So now we need to figure out, given that production function, how many workers and machines do we need to meet a production target of 140 units. So let's take our Q and set that equal to 140. Let me grab my pen. So this was Q, so we want the 140, and here's our production function. We got 10, here's labor to the 1/2, and we're going to put in, because capital, remember capital equaled labor divided by 4. Capital labor divided. So we're going to put in L divided by 4. And then we put in our production quota, or our desired production. Okay, so the first thing that we need to think about here is now we've got L divided by 4 times the exponent 0.5. So we can bring this exponent in to each of these terms. So we're going to have 140 equals 10 times L to the 1/2, and this is multiplied. So now we're going to have L to the 1/2 up here divided by 4 to the 1/2, or 0.5. Okay, so let's expand this out a little bit. Okay, what does this mean? L to the 0.5, whoops, that's pretty bad, equals L to the 1/2. Well, that's something we know, right? Because that is just equal to what? The square root of L. And we can even put the 2 there. But whenever we write L, the radical L, it's implied that this is squared. There's a 2 here, unless we put any other number there. If you never see a number there, it means 2. Okay, so if we write these out, if we just expand this, so this L to the 0.5 is L to the 1/2, or the square root of L. This L here to the 1/2, or 0.5, is L to the 1/2, which equals the square root of L. So we'll put that here, and this is divided by 4 to the 0.5, so this is the square root of 4. Okay, well, what do we have here? Let's look at these two terms. We've got the square root of L. We can, since they're multiplied, we can do L times L. Well, if this is the square root of L times L, this just equals L. And if this is the square root of 4, that's just 2 square root of 2 times 2. Okay, since there's 2 the same here, the 2 comes out, and this just equals 2. So we've got 140 equals 10 times L divided by 2. Okay, we're going to bring 2 to the left-hand side. So we got 140 times 2 equals 10 times L. We're going to divide each side by 10, okay, in order to bring 10 over here. So we've got 140 times 2, that's 280 divided by 10. And then we're going to divide the right-hand side by 10. And if we do that, we get L equals 28. So we need 28 people. And then we're going to go back to our relationship where we had capital equals labor divided by 4. Well, 28 workers tells us that we need 4 machines. So what do we have? Given that production function that we had on the prior page, okay, and we'll talk about, that needs to be accurate, and that's just a multivariate function. Given that production function, given the relationship between capital and labor, 4 machines per worker, and given that output goal of 140, we're going to get the optimal mix between workers and machines of 28 workers and 4 machines. Finally, let's talk about what a nonlinear function looks like. So a nonlinear function can't be expressed. It's not going to be expressed as the form y equals a plus bx. Okay, a nonlinear function is going to have probably some exponent. Okay, the minute that you see an exponent on a variable, you know it's a nonlinear function. Okay, just means it's not going to be a straight line. There's going to be a curve. So in this case, we're going to have, this is just a function that's called, if it's curved out, bowed out this way, we're going to call this a concave nonlinear function. If it's bowed out this way, we're going to call this a convex linear function. So often we'll say, let's, a particular production function or something may have a concave shape or something may have a convex shape. That's just when we talk about concave and convex. Concave, the nonlinear function is bowed out to the left. A convex function is bowed down to the right. Now we got a problem with nonlinear functions. So let's go back. Let's grab this concave function since it's bowed up to the left. And let's say we want the slope of this line. This becomes much more problematic because remember we defined slope is, we had slope is the rise over run, change in y divided by change in x. Well, if we do that between, say, this point here, x1, y1, and y2, x2, look at what we have. There's the linear line, but you've got a nonlinear function. Okay, so we've got a problem. Okay, we can't for nonlinear functions, when we think about slope, we need to use calculus. And here's where we're going to get into the use of derivatives. So we're going to have some, let's first talk about what a derivative is. So a derivative is just a rate of change. Okay, it's going to be a small rate of change. And we're going to denote this usually as dy dx. This just says the change in y that results in a change in x, or dy dx. Or we'll sometimes write this as because y equals f of x, we'll often write the derivative as f prime x. So we can write this as dy dx or f prime x, means the same thing. What's the change in y that results in a change in x? So we're going to have some change in x. What's the resulting change in y? And we are going to be talking about small changes. And we can talk about in class what a small change means. So let's look at some rules, because as with everything thus far, we're going to have rules. So rule number 1 with differentiation. So here I'm going to be thinking about y equals f of x, just because it's easier to write it here. So if I say if f of x equals c, what we're saying is if y equals c, and c is a constant, then the derivative, or the derivative of a constant f prime of x equals 0. Think about what that means, right? A derivative is a rate of change, but a constant doesn't change. So the derivative, right? Derivative is what's the change? So if we look at dy dx, okay, if x doesn't change, why would y change? So if the change in x is 0, the change in y is 0. So if f of x equals 3, then f prime of x, or the derivative the derivative of x, or the derivative of y with respect to x equals 0, or f prime x. Rule number 2, if f of x equals x to the a, so now we've got a is any number, okay, then f prime of x dy dx is going to be a x to the a minus 1. Okay, what we're going to do is we're going to bring this exponent down in front. That's number 1. And then the second thing we're going to do is subtract 1 from that exponent. Okay, so the derivative of x to the a, we're going to bring a down. So now we got a times x, and then we subtract 1, a minus 1. Okay, so if f of x equals x3 and we want f prime of x, 3 gets brought down, and then we subtract 1 from 3. So you get 3x squared. Let's say we had 2x cubed. Okay, so we've got 2 already down there, and then we're going to bring 3 down from the exponent, and then you're going to have x 3 minus 1 equals 6x squared. Rule number 3. If f of x equals c times g of x, where c is a constant, okay, c is a constant, then f prime of x equals c, that constant stays the same, times g prime x. Okay, so in this case, c is just multiplying g of x, where we've got some function of x. Okay, so I'm gonna grab my pen. What do we got? So we've got f of x equals 4x squared. Okay, f prime of x, so the 4 just stays the same. I just did this on the last slide. 4 stays the same, 2 comes down, and then you've got x squared, and then we subtract 1. So this is 8x, 2 minus 1, okay, which is 1. So you get 8x. Okay. Rule number 4, if f of x equals g of x plus h of x, then f prime x equals g prime x plus h prime x. Or if f of x equals g of x minus h of x, f prime of x equals g of x minus h of x. So let's just try this. So let's say g of x equals 4x and hx equals x squared. So f of x equals gx plus hx, okay, or we just have this, okay, which is the equivalent of saying what? Y equals 4x plus x squared, okay, where this is g of x, 4x equals gx, and hx equals x squared. Okay. So if we're going to take f of x, we take the derivative of the first term plus the derivative of the second term. So this is just, there's a 1 here, so 1 comes down. So you get 4x to the 1 minus 1 power plus 2x 2 minus 1. Well, 1 to the 1 minus 1 is x to the 0. Anything to the 0 power equals 1. So this is just 4. Okay. Plus, we've got 2x, and that was 2 minus 1. So this is just 1. So we're left with 4 plus 2x. Okay, so let's do, if f of x equals a plus bx, then f prime x is just going to equal to b. So think what we're doing here. So let's say if f of x equals 3 plus 4x, f prime of x, so there's no variable here. So if there's a constant that's added, it's completely ignored. We've got a 4 here, so this is 4. This is an exponent of 1, so this is 4, 1. Whoops, we'll put 1 here. X to the 1 minus 1. And that is what? 4x to the 0 power. Anything to the 0 power is what? 1. So this is just 4. Okay? fifth rule. This is the product rule. If f of x equals g of x times h of x, so now we're multiplying two functions, or two terms that have variables. What we've got is f prime of x. We're going to have two composite terms. We're going to have g of x times h prime x plus g prime x times h of x. Let me grab my pen. So if g of x equals 3x, hx equals 1 minus x squared, so f of x equals gx plus hx. Okay, so f prime of x. Okay, so let's look at this first term. So this is just going to be g of x, which is 3x, times h prime x. Well, this is 1 minus x squared, so this becomes, 2 comes down, so this is minus 2x. So this is 3x times minus 2x plus g prime of x. So the derivative of this is 1, so this is 3 times 1x to the 1 minus 1, which is 0. So x to the 0 is just 1, so this is 3, times hx, which is 1 minus x squared. So we've got 3x times minus 2x plus 3 times 1 minus x squared. So this is minus 6x squared plus 3, I'm going to bring 3 in here, minus 3x squared, which equals 3 minus 9x squared. If you're not familiar with this, so this has been a long time since you've done this, take a couple minutes and try to go through that, because the product rule and quotient rules are not difficult. They take a few steps. So just like up here we had with the product rule where we had multiplication, we've got two terms being added together. In the quotient rule, we've got g of x divided by h of x. All that's going to do is we're still going to have two composite terms, but now they're going to be subtracted from each other, but then we're going to have a division and an exponent. So the quotient rule can get complicated pretty fast. So here's the formula. So let's say g of x equals 3x, hx is 1 minus x, and then f of x equals g of x equals hx. So this would look like this. It would look like fx equals 3x, 1 minus x. And we want to take the derivative of f of x, so f prime of x. So let's figure out what all this is. Let's just go term by term. Okay, so hx is just this term right here, 1 minus x. Multiply that times g prime x. G prime x, the derivative of this is, remember this is 1, so 1 would come down, 3 times 1, x to the 1 minus 1, that's 0, so x to the 0 is 1, so the g prime x is just simply 3 here, minus h prime x. H prime x, this 1 goes away, and we've got 1 here, so minus 1, or 1 comes down, so we get minus 1x to the 1 minus 1, which is 0, so x to the 0 is just 1, so we're left with minus 1 down here. So there's minus 1 times g of x, which is just 3x, that's here. And we need to divide this whole thing divided by hx, which is 1 minus x, and that term in the denominator squared. So here is our resulting quotient rule if we just follow each of the terms. What we're going to do now is just bring this 3 in. So we've got 3 minus 3x, and this is minus times a minus. This is plus 3x. So there's the numerator, and in the denominator we got 1 minus x squared. And the most we can do to reduce this is 3 minus 3x plus 3x. These go away, so we're left with 3 divided by 1 minus x squared. So let's go back to thinking about the slope. Okay, the slope of a nonlinear function. So what we're going to do is we're going to let's say we're interested at y1 x1. So the slope of the line here, what we're going to do, or slope of this nonlinear line, okay, this nonlinear function, which is that blue curve, at x1, y1, we are going to impose a linear function tangent to that point, okay? And what we're going to do is we're going to look, and this is why the derivative is small, okay, small changes, because when we talk about a small change, what we're really doing is we're approximating the slope of a nonlinear function with a linear line. That's why it has to be a small change. Okay. If we have a nonlinear function that looks like this blue line, okay, and we take the slope, or the slope of this nonlinear line, okay, the derivative of a nonlinear function, say at point A, okay, this is going to be positive. Okay, this line is going to be sloping up. Okay, if we're here on the right-hand side at C, the slope of this line, okay, the derivative of this line is going to be 0. It'll be less than 0. And right here at its maximum, okay, or minimum for that matter, okay, at its maximum or minimum, if we take the derivative right at B, the derivative of this nonlinear function at B is going to be equal to 0. And we'll see some examples of this when we get into, and certainly into economics. Let's do an example, okay? And these are going to be the example of what we have here. We've got cost functions and marginal cost functions. So in economics, we're going to refer to the derivative of the total cost function as a marginal function. So we're going to have total costs and total revenues, and we're also going to have, if we take the derivative of the total cost function, it's going to give us marginal cost, or if we take the derivative of the total revenue function, it's going to give us marginal revenue. And all that means is the following. Remember the derivative is a small change. So if we have a total revenue function tells us what's happening to total revenue. If I take the derivative of the total revenue function, I'm going to get something called marginal revenue. What that's doing is I'm looking at what's happening on the margin, a small change. What happens to revenue if I sell one more unit of a good? If I sell going from 100 to 101 unit, that additional unit, how much does that add to margin? Or how much does that add to revenue? That's marginal revenue. Okay, this example here is we've got a total cost function on the bottom. Total cost, you'll sometimes see this is C as a function of Q equals 2Q squared plus 200. Okay, that's a total cost function for a given output. That's nice, but if I'm interested in how much does it cost me to produce one additional unit of good, that's going to be marginal cost. So I can take the derivative of the total cost function. Okay, if I do that, that's C prime Q. So let me grab my pen. If I take the total derivative I take the derivative of this function, this is a constant, so that goes away. 2 comes down, so this is 2 times 2 times 2 times Q. I'll put 2 times 2 Q 2 minus 1. So what is that? 4 Q 2 minus 1 is just 1. So you get 4Q. Okay. So when you'll see this notion of we're going to have these big functions, these cost functions and revenue functions, but in reality, what we're going to care about is what's happening on the margin. Finally, we need to talk about what's called the partial derivative. Okay, what we just went through was the total derivative. Okay, but now let's talk about something what's called the partial derivative. And let's say, suppose that we've got y as a function of more than one variable. Let's say x and z. Okay, so that we've got f of x and z. The partial derivative is going to tell us how the function changes, okay, as we change one variable, holding everything else constant. So if we take the partial derivative of x, or partial derivative of f of x of z, okay, and we've got given a change in x, or in the second case, we got the partial derivative of f with respect to z. Okay, in this first case, what we're interested in is what's happening to that function if we hold z constant and we change x a little bit. That second partial derivative is asking what happens to our function if we hold x constant and we change z a little bit. Okay, so let's do this. So let's say we've got f equals, f is a function of x and z, and it equals 4x squared plus 3xz. Okay, then the partial derivative with respect to x is the partial derivative sine f of x and z, okay, given with respect to f, or with respect to x, I'm sorry. So let me grab my pen. So we're going to be, if we're looking with respect to x, small changes in x, okay, and we're holding z constant, z just gets treated like a constant. It's just going to hang out. Okay, so let's look at this first term. Okay, 2 comes down, so you get 2. So if we put 4 over here, times 2, x, 2 minus 1, okay, and that gives us 8x, this term here. And then over here we've got 3x and z. So z is just going to hang tight. Z is not changing. So we got x to the 1. 1 comes down, so you got 3 times 1 x, 1 minus 1, 1 minus 1 times z. Okay, this is 0. So this is, I'm sorry, this is 1 minus 1 is 0. So x to the 0, that's just 1. This is 1, so you got 3z, which is here. Okay. So partial derivatives we'll use when we have large functions, okay, multivariate functions, and we're interested in just changing one variable, in this case x, and holding z constant, or if we're interested in changing z, holding x constant. Let's finish up with this last section talking about exponential and log functions. We'll touch on these a little bit in economics, but where you're really going to see this stuff is going to be in corporate finance, and it's at the present value calculations. So let's touch on it now. And when you just remember, before you take corporate finance, I'd really highly suggest you flip through the chapter in the book, the Trevitan book that you have. Okay, so let's start with this. Exponential function is going to have the form fx equals bx, where b is a constant and two things hold, b is greater than 0 and it doesn't equal 1. Okay, notice the difference. We just did power functions where f of x equals x to some power, where this was 2, 3, 4, 5, or 6. Now we've got an exponential function where these things are flipped. So now you've got the variable up here in the exponent, and b is some number. Okay, so we just did power functions, and now we're talking about this thing up here called an exponential function. Okay, lots of numbers can be used for b, but e has a special place in mathematicians' hearts. Okay, and it's going to be it's the most common number that gets used for b. E is an irrational number, and it approximates 2.718. Okay, so since the exponential, since e gets used a lot in what's called exponential, let's talk about some of the properties of e. Okay, so e to the x is always positive. It has to be, because if e approximates 2.718, yeah. So if e approximates 2.718, 2.7, let's just call 2.7 an x. Okay, this is always positive, because there's no negative there. So this has to be positive. Okay, it's always positive. Okay, e raised to any power can never equal 0. Okay, because e to the x equals 0 has no solution. Okay, and we'll graph that, and you'll see why. E to the 0 is just 1, because remember, anything. So even if this is x to the 0, okay, back into the power functions, x to the 0, 10 to the 0, 10 to the 0, e to the 0, this equals 1. So that rule doesn't change. So as x gets smaller, okay, so is this exponent, as x gets smaller, okay, the value of ex approaches but will never, ever reach 0. In other words, we would say e of x is asymptotic to the x-axis on the left. Okay, so let's graph it. So now we're going to do a full 4-quadrant graph. So here's our vertical axis Y, or horizontal axis X. We're going to have 4 quadrants. Okay, positive quadrant X, Y. This is the one that we're playing with our supply and demand. We were over here in quadrant 1, but you got quadrant 2 where you got negative X, Y, quadrant 3 negative X, negative Y, and quadrant 4 positive X, negative Y. So let's draw what E of X looks like. And this is what it's going to look like. So E of X is going to come and it's going to come down and it's going to get asymptotic, but it will never, 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 never touch the x-axis. Okay, so let's use the corporate finance example, continuously compounded interest. And that formula is going to be P times E to the RT. Couple slides. Sorry. Let's talk about log forms. Okay, so that was the exponential. So we're going to have a companion to that, and that's going to be a log function or a log form. Okay, so the inverse or the opposite of the exponential form is going to be called the logarithmic function. And this expression we're going to write log bx equals y, and we'll read that as the logarithm of x to the base b equals y. So when we write log bx equals y, again, we'll read that as the logarithm of x to the base b equals y. Okay, and the most common form in economics and finance, since we're going to use e, is our base of the logarithm. So if we write log base e, if I write log of x base e, so b equals, so this b is e, this has a special form, and we call this the natural log. And we're just going to write that as ln of x. Whenever you see ln of x, what that really is the logarithm of x to the base e. Okay, it's this. The logarithm of x to the base e equals something. Okay, and again, we're just going to write that as the natural log of x. And this is the most common form that you'll see in economics and finance. And since it is just like e, let's talk about some properties of the natural, what we'll call the natural log. So since these are opposites of each other, if we take the natural log of e, okay, it's just going to equal 1. They're opposites of each other. If I take the natural log of e to the x, okay, this is going to equal x. So these kind of cancel out, and the power and the exponent comes down. So if this is the natural log of e to the 10x, this just becomes 10x. Okay, natural log of 1 is 0. The natural log of two variables multiplied together, we can distribute that natural log. So it'll be the natural log of x plus the natural log of z. If we have the natural log of x to the z, we can pull the exponent out front. Okay, so this z can come out front, and we have z times the natural log of x. Look at the graph over to the right. Okay, so we're going to have a 45-degree line here. Okay, and here was our exponential function e to the x. Okay, and we're going to have the opposite, the log function, the natural log of x. Okay, so if they're literally mirror images of each other around the 45-degree line. Let's do a problem. Okay, let's do an example. Final example. Let's say we've got an investment, so the doubling time for an investment. So what we're going to look at. Let's say we got $500 is invested in a money market account that pays an annual interest rate of 5% compounded continuously. Yes, this is wishful thinking. How long will it take in our fairy tale world to double our money? Okay, well, there was the example that we were going to show you on the prior curve. Okay, that's back here. If we go back here, So here is P times E to the RT. If we plot that, we're going to have this, and it'll never touch the x-axis. Okay, so we're going to be using this continuously compounded interest. So we've got P equals E to the RT. Okay, well, P is our principal, so $500 times E. R is interest rate, 5%. T is time. Okay, how long is it going to take to double? So that would be $1,000. Okay, so let's take 500 and bring it over to the right-hand side. So we're left with E to the 0.5t equals 2. Okay, now we need to get rid of this E. Well, we can do that easily, right? If we take the natural log of both sides, remember what happens? We take the natural log of both of these. We're just left with the exponent. It becomes 0.5t equals the natural log of 2. Divide each side by 0.5, bring that over, and we're left with t equals the natural log of 2 divided by 0.05. This you need a calculator for, and this will give us 13.9 years. So if you put $500 into a money market account that paid 5%, your money would double from $500 to $1,000 in nominal terms in 13.9 years. Okay? If you have questions, email me. Okay, I will see you all in the fall. Again, I would highly recommend you read those first 2 chapters. I think I say in the note there's one section not to read because it's not relevant. Take a crack at the 10 practice problems. If you can clear those 10 practice problems, you should be fine in terms of your math skills for the MBA program. You're going to certainly have to use probably a finance calculator or a computer when you get to corporate finance, but the algebra, the basic algebra and the basic calculus shouldn't be difficult for you. If you're struggling, read the book, go through this lecture, try to do some of the problems. You've got the additional links, so if you need more than that, try the Khan Academy. If you still need help and if you're struggling, email me a question. I should be able to just respond. Or secondly, if you're working on the problems and you're stuck, even though I gave you a solution set, don't look at those. Look at the problems first and try them. And if you're getting stuck, feel free to scan it. Send me your chicken scratch. I'll print it. I'll give you my chicken scratch and I'll scan it back. And hopefully we can get you on the same page. Again, congratulations on your admission to tech, and I look forward to seeing you in the fall.